Here's part 2 of chapter 3. We're going to look at percent composition and empirical formula. Percent composition is a mass relationship. We're looking at the part over the total. It's basically a percentage of each of the elements' mass compared to the total. If we look at an example we've already talked about before, we'll look at calcium carbonate. So calcium carbonate has a molar mass. We show all the molar mass work. Now all we do is we take the part that's calcium, 40.1, divided by the total mass. Since the total mass is 100, it works out nicely. We'll get 40%. We do the same thing with carbon. Carbon's mass, 12.0, divided by 100, times 100 to turn into a percent, 12.0. Now the oxygen was 48, divided by 100 times 100, 48%. We can add them up, and we should get 100%. We do. So if we had a sample of calcium carbonate, it would be 40% calcium. It'd be 48% oxygen, 12% carbon. All right, let's look at another example, magnesium nitrate. Same idea here. We've done this one before. We get all their masses. And now all we need to do with our mass from the magnesium, 24.3, we're going to divide by the total, 148.3. We'll get 16.3%. Same thing with the nitrogen is 28 divided by 148, 18.9, 96 divided by 148, 64.7. We add them up, 99.9. That's good. I know it doesn't equal 100. That's because we rounded these values off to one number to the right of the decimal. If you get less, you should either have 99.9, 100, or 100.1%. If you don't, you round it off either incorrectly or you did some work wrong in the problem. Common thing that you'll be asked to do is to calculate the percent water in a hydrate. We know hydrate is just a salt. In this case, it's copper sulfate with a certain number of hydrates or a certain number of water molecules bonded to it. So first thing we need to do is figure out what the formula is for copper 2 sulfate heptahydrate. Copper 2, so that must mean it's Cu with a 2 plus charge. Sulfate, I remember, has the ATE, so it's one of those polyatomic ions. Remember that it's SO4 2 minus. Since the charge is equal, I can just write Cu SO4. Now heptahydrate. I remember from my prefixes that hepta is 7. And then for the hydrate, we just write H2O. And there's our formula for the hydrate. Now, I'm going to give you a minute. Actually, we'll go through this one together. So here we have it. I can write or get my molar masses from the periodic table. How many atoms are in each. What I'm going to do is I'm going to keep H2O as H2O. I'm not going to break that apart. I know there's oxygens here and oxygens here. What I'm going to do is keep my water as one unit. We know the molar mass of water is 18. There's 7 of them, 7 times 18. So we can get our total. So now for the percent of copper 2 sulfate heptahydrate that is water, we take our water amount and we divide it by the total. So now we have 126 over 285.7 times 100, 44.1%. A common lab that we might actually do is we'll take a hydrate, we'll put it in a crucible, we'll heat it up, or even a test tube, heat it up, drive all the water away. We mass it before and after, and we see what amount of water was released. And from that, we can go back and figure out what hydrate it was, whether it was a pentahydrate, a tetrahydrate, or what. I'm going to give you a minute right now to calculate the percent water in barium chloride dihydrate. Again, start with the balanced formula, or balanced formula, and then show the molar masses and calculate the percent of water that's in there. Again, keep water as one unit. Why don't you pause the video right now and calculate that. All right, you had a minute to do that. hopefully you first came out with the that the barium chloride is BaCl2, 2H2O. So what we have, we look at the molar mass of barium, the chloride, and the water. We get our part for the water is 36. Our total was 244. Divide them times 100, 14.7%. So if you had a sample of barium chloride dihydrate, 14.7% of it would be H2O, water. All right, these are mass relationships. We're now going to look at empirical formula, which is a mole relationship. So let's look at our example here. Empirical formula is the simplest, most reduced formula. So if we had something like H2O2, that's hydrogen peroxide, its empirical formula would just be HO, the simplest whole number ratio. Let's take a look at this example. An 11.5 gram sample of liquid contains 6 grams of carbon, 1.51 grams of hydrogen, and 4 grams of oxygen. What is the empirical formula of the liquid? Again, I said this is a mole relationship. So the first thing we're going to do is take our grams and convert them into moles. 6 grams of carbon, molar mass is 12. So I get 0.5 moles of carbon, 1.51 moles of hydrogen, 0.25 moles of oxygen. Now I can't stop here because we don't write our formulas as C, 0.5, H, 1.5, O, 0.25. We always put whole numbers into our formulas. That's 1.5. There's a real simple way to get these values to be all whole numbers. What we do is we divide each number of moles by the smallest number of moles that's there. And this will give us our whole number ratio. So out of these three, the carbon, hydrogen, and oxygen, the 0.25 is the smallest number of moles. So what I do now is I take my moles of carbon, 0.5 divided by 0.25, gives me 2 moles. Hydrogen, 1.5 divided by 0.25, gives me about 6 moles. Oxygen, 0.25 divided by 0.25, gives me 1 mole. So now this is my empirical formula. This is the simplest ratio of atoms that I can have to each other. C2H6O.